Hi everybody, in this video I'll talk about how to graph a quadratic function from a table. There are many methods to graphing quadratic functions that do not involve a table, but we will not look at those today. We will look at those in another video. Specifically, a table is probably one of the easiest ways because it relies on your most basic knowledge of substitution and evaluation. So I think that's why it's a good place to begin. In my future videos, I'll talk about other methods, so please be on the lookout for those. But in the meantime, let's go ahead and just talk quickly about what a quadratic function actually looks like. And it looks like this one over here in red. Now, this particular form is in standard form. And the reason it's called that is because it goes from highest to lowest power. And, uh, and so a couple things that you want to note about this is that if I were to cover that ax squared, which I'll do by simply erasing it, if I were to cover it like that, what you would have is something that is a linear equation. So this would be the equivalent of y equals mx plus b. And it is in fact the very same thing, where this last constant represents the y-intercept, if you remember that. But because we're dealing with a quadratic, we have an extra part to consider. However, this last constant still represents the y-intercept. Okay, and because of that, quadratics are very generous. They give you a free point to begin with, and it's whatever number this is, positive or negative. There are basically two types of parabolas that you look at in an Algebra 1A level course, and they look like this. In terms of how they look, there are two types. So one is a smile, one is a frown. Regardless of what it is, both parabolas have a vertex. Now the vertex is going to be either the minimum or the maximum. On a smile, like this one here, the vertex is all the way at the bottom and it's the lowest point on this parabola. So it is a vertex, but it's called a minimum point. On this one, the frown, the vertex is at the very highest point. And so this is called a maximum. So the vertex is a maximum when it's a frown. Both types of parabolas have what are called axes of symmetry. And that's simply an imaginary line that divides a parabola into two equal parts. Now, the equation for the axis of symmetry would be something of a line, because this is an imaginary line. But what's important to note is that this line always cuts right through the vertex, because this is the very middle part of a parabola, where it switches directions from going up, in this case, to going down, or going down, in this case, to going up. So it's your switch point. And for that reason, the axis of symmetry always slices right through that, and it divides a parabola into two equal parts. So the equation will always be x equals and then some number, but a little tip is that the number will always be the x coordinate of the vertex, since that's the point through which it goes. So we'll look at that in a little more detail coming up. So here's example one. In example one, I want to graph this function right here. Now, a couple of things you want to see about the space given to you. First of all, you will not always be given a coordinate plane to work with. Sometimes you have to make your own. But if you're given a space to work with, it's a lot more convenient, because then you can pull information from this to use in your table. The first thing that I notice is that this is heavily concentrated on quadrant 4, which means that a lot of my y numbers are negative and my x values are mostly positive, 1, 2, 3, 4, 5. I have very little above the x-axis and very little to the left of the y-axis. So most of my graph will be contained in this space right here. Okay? So when you're doing a table, like this one over here, it's a good idea to expand it so that you have both a function and a space for the ordered pairs. Now, the input values you want for the x column would come from the x coordinate, or excuse me, x-axis on the graph, or excuse me, on the coordinate plane. So if you look here, the numbers are given to me to use. Because my graph will be around here, I can borrow these numbers 1, 2, 3, and just drop them in. So 1, 2, 3. Okay. If you need more later, you can use more and stretch out your table. But remember that sometimes you get extra points for free because of that axis of symmetry behaving like a mirror. So let's go ahead and plug these in and see what we get. Oh, I should mention that we do, again, have a free point, which is that y-intercept. But unfortunately, I don't have space to actually put the point there. As you can see, the highest I get is 1. And I don't want to stretch it out and guess. I want to know exactly where things are going. So just an FYI for the future, always look to that. If you have an opportunity to put it, put it. Otherwise, go straight to the table. And here we go. So this would be the following. It would be 1 squared minus 6 times 1 and then plus 5. So breaking this down, this would be 1 minus 6 plus 5. And putting all three numbers together, that would be a 0. Okay? 1 minus 6, negative 5, plus 5, 0. So my ordered pair is 1, comma 0. So I can go ahead and put that 1, comma 0 will be right here. My second point would come from 2. So I would use 2, put 2 squared minus 6 times 2 plus 5. 2 squared is 4. Negative 6 times 2, negative 12 plus 5. Putting all these numbers together, these two make negative 8 plus 5 is negative 3. So my coordinates are 2, negative 3. So 2 and then negative 3 right here. My next one would be 3 squared minus 6 times 3 plus 5. So this would be 9 minus 18 plus 5. 9 minus 18 is negative 9 plus 5 is negative 4. So my ordered pair would be 3, negative 4. And so that would be 3 and negative 4, which would be right here. Now, I don't have a complete picture. And so in this case, I would need to stretch my table and generate a few more points from it. So I'm going to stretch this out, and I'll put you know what? I'll put the number 4 to see what happens. It could be that this is our vertex, and from here it's going to swing up, but I just want to be sure. So let's go ahead and see what happens when I put in 4 squared. This is 6 times 4 plus 5. This is 16 minus 24 plus 5. And 16 take away 24 is negative 8 plus 5 is negative 3. And aha, I've seen that number before, right over there. So as soon as numbers repeat, you know that you're on the other side of that parabola. So my ordered pair would be 4 comma negative 3. So 4 comma negative 3 is right here. And what that means is that my vertex is actually right here. Okay, so that would be my lowest point. So this is my switch point. My vertex is at 3 comma negative 4. And for that reason, I can kind of figure out where my axis of symmetry would be. It's the line that cuts right through the vertex. And now that I know where my vertex is, my axis of symmetry is here. And the equation for that would be x is equal to, and I take the number 3 from the vertex, right? So my x coordinate becomes the equation for my axis of symmetry. X is equal to 3, because it's always 3 spaces to the right of the origin. And so now each point behaves like a reflection of itself. So this point here will have a double, but on the other side of this axis. This is like a mirror. So if this is 2 spaces away from the axis, then its reflection will be 2 spaces on the other side, putting it about right there. And with that, I can go ahead and complete the graph. And when you draw this parabola, you want to make sure it doesn't come out looking like a letter V. That would be wrong. That's actually the graph of absolute value. So the graph of a parabola always looks like a letter U, and it has a nice curve at the bottom or at the top. So I'll do the best that I can. Let's see if I can pull this off. Swing it up. Make it as even as you can. Okay, and I don't want to go beyond the boundaries of my coordinate plane. Even though I know that it does go on forever, I'll just put an arrow right there and stop it. Okay? Again, you don't want to assume where things are going. You want to actually know. So there's your parabola. So it's based on the idea of substitution of values from the very coordinate plane that you're given itself. Okay? So I borrowed numbers from the x-coordinate, the x-axis, excuse me. I borrowed those numbers, put them in the table, and then one by one, plugged them into the function, did my math, got my output, paired up my input with my output to get my ordered pair, and one by one, I turned each ordered pair into points, which I then connected. And as soon as I knew that a number repeated, like -3 for my output here, -3 for my output there, as soon as I saw that, I knew exactly where my vertex would be, because it's going to be in between those repeating numbers. Okay? And the vertex, as a last note, is the only point that does not have a double, because it is the lowest or the highest point on the parabola. And it's a place that the axis of symmetry cuts right through. So it is a point unto itself, whereas all the other ones have duplicates. So I hope this video helped you out. I will have a follow-up video with a second example in case this was not enough for you. But as always, please stop by, leave a comment, and thanks for watching. Bye-bye.